Hello everybody. Last week we started talking about corner detection, Harris corner detection. We derived uh, equations about the corner detection. At the end we came to a matrix which is called an Hessia Matrix. Okay. Something like this. This was all the
Hocam sesiniz kapalı kalmış.
So last week we started talking about Harris corner detection, and we derived all the formulations for the corner detection. We came to this matrix. This matrix is summation of the at the corners, summation of the vertical, horizontal gradients, horizontal derivations, and vertical derivations, and then multiplication of these, okay, at the corners. Then we said that u times c, or maybe I should do it this way. I should multiply this one with uv, and then uv, and this is our EUV formula, and we said that this matrix C is independent of the UV position. It depends only the part of the image that we are looking at, and that's a very good observation. Then we said that this is like a ellipsoid formula actually. This is like a square plus ax square plus b xy plus cy square kind of formula for ellipse. And we said that the eigenvalue analysis or the finding of the eigenvalues of this matrix is the solution for our corner detection. If both eigenvalues are high, larger than 0, then we say that there is a corner. Otherwise, maybe there is a edge or constant region. We talked about this. That was the Harris corner detection. And at the end, I showed you, I think I showed you this. We said that, okay, so this is what you do. Take these lambda values, eigenvalues, and alpha is a constant, usually chosen as like this. Okay, calculate this one. If this one is very small, it's a flat region. If it is large, then it's a corner. If it is less than 0, it's an edge. We talked about this. And usually we don't calculate these lambdas directly. We calculate these values actually. All the x gradients, y gradients, squares, and minus the multiplication of x and y gradients, and minus this. Okay, so this is the threshold, this is the calculation, and we do the non-maximal suppression. That's what we get. And this was one example, the same scene taken with two different camera views and different lighting, and it works. We take this, and for each point we calculate the C threshold. Okay, we calculate the C and we pass it through a threshold, and we get this. After non-maximal suppression, we get these points. We get these points, and these points correspond to each other. Okay, let me show you both of them in the same screen. Okay, so this one is like, no use this color, something like that, right? So these are the feet, and goes like that. Okay, and this one is a little bit different. Why? Because this one is rotated. Something like that. Okay, so I can do the correspondence between each other, and I can get the correspondence between these two images. Question: using these points, okay, if I find the corresponding point, let's say this point corresponds to this point, this point corresponds to this point, and then let's say this point corresponds to this point, and one more let's say using the, and this point corresponds to this one corresponds to this one, etc. So I have found, let's say 4 or 5 correspondences between these two images, like that. Okay, can I establish a homography between these two? Can I establish a homography matrix H, a 3 by 3 matrix between these two images?
Sorry, I missed. Do we have 4 points?
You can have as many points as you like.
In homography, we need only 4 points to calculate homography.
Well, you can have as many points as you like. 4 points, 5 points, 10 points, doesn't matter. For the homography, we need at least 4 points, yeah. But if you have more than 4 points, that's okay. We are going to use it in a least square sense, and that's going to be fine. The question is, doesn't matter how many points you have, can I have an homography between these two images, saying, let's say, if I have an homography between, let's say, like I1 and I2, okay, let's say this point here, I know that it corresponds to this one. Using this homography, let's say if this is a point X, if I multiply X with H, can I get X prime?
But are they same pictures?
What do you mean? Yeah, they are the same, yes.
From different perspectives?
Yeah, it's like your homework.
So
It's like homework. I mean, the same scene taken with 2 different views.
Then I think we can, but if you ask, probably we can't.
Well, yeah. Well, the second part of your second part of your answer is correct. If I am asking this, then the answer must be no. But how come it's no? Remember, under what circumstances we have the homography between 2 views? If the things are planar, okay? If there is a plane involved. Without the plane, you cannot have a homography. And I don't have a plane here, okay? I don't have a plane. I cannot have a homography between these 2 images because their depths are different from the camera. Because this toy has a depth. It is not a picture, okay? It has some depth from the camera, and it is different. So that means what? That means there is no way that I can get this image out of this image. They are different. I mean, logically, it is true. Why? Because if I can get this image out of this image, then that means that using homographies, I can produce any views that I like, right? That's not that easy, no. No homography or no linear relationship would produce an arbitrary other view of the same scene. Okay, so this is not possible. Well, in our homework, it was possible because our target was a plane of the soccer field, right? But in this case, we don't have it. Good. Okay, so this is good. We liked it. Why do I use such correspondences between those? We have lots of cases for the correspondences, not for just for homography, and we are going to see it later. So we like this one, but Harris detector has some problems. Problems are problems are these. We like Harris because Harris is invariant for the position in the image. Doesn't matter if my corner is here or there, I will find the corner. Okay, so because I am just using the derivatives, okay, window functions, and they are shift invariant. So Harris is nice. It is invariant against the position in the image. Anywhere my corner is in the image, I will find it. Doesn't matter if it is here or there. Okay, I will find it. So corner location is covariant with respect to translation. How about rotation? Rotation is the same. I mean, the matrix that I am going to get for this corner and this for this corner will be different, but their lambda values for these ellipses will be the same. Okay, so remember that the ellipse formula that we have, that we did, uv times c times uv. This is an ellipse formula. Okay, the ellipse formula that I am going to get for this part of the image and for that part of the image will only differ with respect to their angles. Okay, their lambda values, that's the radius, the small radius and the large radius will be the same. So rotation, we are okay. Second moment, ellipse rotates, but its shape remains the same. So corner location, Harris corner location is covariant with respect to rotation. So I can find it. I can find it, no problem. But when it comes to the scaling, for example, this is my corner. Okay, this is my corner, and if I calculate all of my I x and I y values for this window and calculate c and calculate those lambda values, lambda 1 and lambda 2, I will find that there is a corner. Okay, I know that. But if I make this corner larger, if I scale it up, let's say my corner is now like this. Okay, it's the same corner, only I scaled it up. If my window size is small like that and like that, and if I divide this into these windows, okay, and the C matrix here, C matrix there, and C matrix there, will not show me any corner. So unfortunately, our Harris corner detector is not insensitive to scaling. If you scale, sorry, I have to take this. Efendim? Buyurun. Teşekkürler, siz nasılsınız? Herhangi bir mail değil, link, katılım linki gelmedi. Daha önceden şey geldi. Bir dakika. Bana 2 Nisan'da bir mail gelmemiş ya. Bana bir sizden 2. ayın 19'unda gelmiş. 2. ayın 19'unda doçentlik sözlü sınavı diyor. Bahsettiğiniz adayla alakalı bir PDF dokümanı ve içerisinde sınav bilgileri var. Tarihi ve 14 Nisan 10 yazıyor ama buranın üzerinde bir link falan göremiyorum bu dokümanın içerisinde. Yok, ben de Yeşim'di değil mi sizin isminiz? Soyadınızı alabilir miyim Nurgül Hanım? Nurgül arıyorum. N-E-U N-E-U diye aradım. Hayır, ben de maalesef 2 Nisan'da NEO'dan gelmiş bir mail göremiyorum ben ya. Aha, tamam. Teşekkürler. Evet, Akkul. Aha. Hı. Teşekkürler. Sağ ol, teşekkürler. Sorry for that, I had to take it. So did you so it is not scale invariant. We are sensitive to scaling. That means that if my window size, if my corner detection window size is this small, I cannot detect this large corner. If the corner is small, then I can detect it. But if the corner is large, then I cannot detect it. So what am I gonna do? I need a window of like this size. Okay, so that's a problem. That's the motivation of SIFT, actually. Okay, that's the motivation of SIFT. With SIFT, we say that Harris operator is not invariant to scale and correlation. Harris operator is not invariant to scale, and correlation, remember the correlation is not invariant to rotation. Okay, for better image matching, the inventor of SIFT, this guy Low, he said that he's going to find the interest point detector that is invariant to scale and rotation. So he likes to do whatever Harris corner detector can do, plus he wants his detector to be invariant to scale. Also, law says that there is a descriptor for the interest point. Remember, this was our results from the Harris corner detector. It says that I found a corner here. This is a corner. That's a corner. Let me use the green. Green is more. No, not good. I think red. Red is not good either. Okay, let's use green. These are my corners. And that's it. I would get X and Y positions of these corners, and that's it. How do I match this X and Y position with this A plus Y plus position? Efendim? Şu anda geldi, evet Nurgül. Erişim adresi diyor. Evet, aç. Bir dakika. Ne diyor? İlk önce bir açılamıyor dedi ama başında bir şey olduğu için bir dakika, ben bunu bir yere yapıştırmam lazım. Çünkü başına sonuna şey işareti konulmuş. Evet, geldi. Hı? Geldi. Hı. Aha, bağlandı. Teşekkürler, iyi çalışmalar. Okay, so how do I match this xy with this x prime, y prime? Okay, one thing maybe it could be, you would say that, okay, this is an xy, this is x prime, y prime. Maybe I can take this window around this xy and match it with this window using the, let's say this is W1, this is W1 and W2. So I would say W1 XY and W2 XY. So I would take just the difference between these two. Okay, move it here. Okay, I would just take the difference and sum it on all x and y's, and if this fits, then I'm fine. What is the problem with this approach? What is the problem with taking the difference between these two? And if the difference is so small, I would say these two windows are very similar and that's a match. So what is the problem? Anybody? Niyazi, do you have any ideas? Last time you never answered me. Niyazi Mehmet. So Niyazi, you are not attending the classes, but you are just logging in and that's it. Niyazi, are you there? Anybody else? Well, if nobody is answering me, then let me kick Niyazi out of the meeting. If he's in, he will log in back. Okay, if nobody answering me, I will have to go back to Doha. Doha, I am back to you.
Hello. I think I miss what W1 and W2 is.
W1 is this, W2 is this. There is blue windows. I am trying to see if these two windows match. I am trying to find the correspondences between these two images. How am I? Okay, I run the Harris corner detector. I found 100 corners here and 120 corners there. I need to match each corner to somebody else in the other image so that I find the correspondences. How am I going to do that?
But we are all looking for coordinates.
Yeah, well, this one is x and y. This one, let's say 100 and 120. This one is, let's say, 120 and 107. So by looking at the coordinates, I cannot make a match because they are not supposed to stay in the position, right? Otherwise, correspondence would be very easy.
Is the window size fixed?
Yeah, with the window size, you are free to select any window size you like. 7 by 7, 9 by 9, doesn't matter.
When transforming, maybe we should make the window size.
What do you mean transforming?
For example, in the correspondence, the distance between 2 points might be much higher, maybe. So
I don't have the correspondence. I mean, these two images, I did the corner detection. One of them produced 100 corners, the other one produced 120. Now I like to know what correspondence does this corner have in the other image? Does it have any correspondence? Or if it has, which one?
The one contains the one that is in the window in that corner, the other corners, right? So if that window has maybe other corners.
No. I mean, see this one here, the new one. This one When I look at it, the corresponding point is way over here, right? These two correspond to each other, but their positions are so different.
Yeah, but they still, the window they contain still have the same corners in them, right? The window they.
The first window is here, the second window is here. Position-wise, they are very, very different.
Yeah, but if there is another, if the window is large enough and there are another.
No, you are missing this. This window is not a search window, okay? All I am saying is that to be able to match this point with this point, I am comparing these two windows. If window 1 is same as window 2, then I would say that these two would match, right? This is not a good idea, that's what I am saying. Why, and the question is why it is not a good idea?
Because of the pixel values may change.
Because the pixel values are so different. Why are they so different? Lighting is different, and even if the lighting is the same, as you see, the foot, okay, the foot is rotated, right? The foot is rotated. I mean, if you take this window 1 and if you take the window 2, okay, the foot is rotated. So this is not a good idea to make a match. What I am trying to say is that the idea of Harris is this: first, find the interest point. Second, okay, produce a descriptor for that point. That descriptor is going to be 128 dimensional vector to represent that point. And if I like to see if P1 is the same as P2, all I am going to do is just take this difference between these two 128 dimensional descriptors of these 2 points, and if it is close enough, and I will say that, okay, these 2 points are the same. Okay, so that's the descriptor part. Okay, and in fact, the most frequently used part, the most popular part of the SIFT descriptor is the SIFT interest point detector is the descriptor part. Okay, yes, Yusuf.
I missed. What is the descriptor exactly?
When you find a corner, this is the corner, right? This is the corner. What do you have in your hand as a corner? Okay, you have its x and y positions. That's it. What else do you have? Maybe the matrix C, maybe the lambda 1 and lambda 2 values, right? That's it. You don't have any other information about that point. SIFT descriptor says that I will give you the interest point, for example, this one, and also I will give you 128 dimensional vector. That 128 dimensional vector will represent that point. Okay, if you like to compare this point with other points in the other image, compare these 2 vectors. These 2 vectors will be independent of rotation, scale, and position in the image.
Okay, now it's clear.
Okay, that's what we call descriptors. SIFT is good for finding the position of the interest point, plus it is good for providing such a descriptor. In fact, the descriptor is the most used part of SIFT. Okay, some people do this. Some people find the Harris corners and then use the SIFT descriptor around those corners. Some people do this, okay, for matching between 2 images. Okay, any questions? Okay, good. Okay, I will continue. It looks like, I don't know, I mean, I am asking question and nobody seems to giving me answers and nobody is yet asking me questions. I didn't understand that and that. I think I do the same thing in the morning. I think I will give you a small quiz, okay? After I am done with this lecture, the first part, at 14:30, we will start a quiz. Small quiz, just 2 or 3 question quiz. And I will ask you a few questions, see what you guys are giving me. So there are now how many people in the, this is interesting. So there are total of 22 people. Let me see how this number increases. People start coming into the lecture.
Can I ask a question?
Sure.
So the distance between these two vectors, these two indicators.
Yeah. Descriptors.
Does it matter if it's Euclidean or other?
That's another topic. Yeah. How do you compare these two distances? Is it L1 form, L2 form, L3 form, or the Manhattan distance? Yeah. But usually we use the L2 form, Euclidean distance. Sometimes people use cosine similarity, the angle between these two vectors. Okay. Okay. So SIFT doesn't tell you how to compare these vectors. SIFT tells you how to extract these descriptors. So okay. So that's the idea. So the idea of SIFT is this: you find your interest points on this image. You find your interest point on this image. SIFT will tell you that I find the interest point here. Its orientation is this way, and it is this large. So it will tell you the orientation and the size of the interest point. Here, the interest point is this way, okay, the orientation. Size is this much, and the position is here. Okay, so that means that I can rotate this yellow window to right up and scale it to a standard 10 by 10 image. Here, I did the same here, same here, same here, same here. So they are all same size and their orientations are the same. If I run the SIFT descriptor on this image, remember this is a very different image, but I have the same object. Okay, since I have the same object, I will get this point, and this point same as those. But I can now compare them. Why? Because I know their direction, I know their sizes, and I can match them. Okay, so at the end I would say that in this image this point matches to this point matches to this point, and this point matches to this point. Even though there is a scale difference between these two images, okay, and there is a rotation difference, lighting difference between these two images, SIFT does its job. It does its jobs. First, it finds the relevant points, finds the correspondences, and second, by looking at the descriptors, I can say that this point corresponds to this one. Okay, that's how SIFT works. Good. Okay.
A question.
Sure.
Well, this SIFT is a vector that contains the information of that yellow
Window.
square.
Uh-huh.
But where do we find 128?
Elements of that vector, I am going to talk about it. Okay. I didn't tell you that yet. That's one of the most important contributions of the SIFT technique. It is how you form this 128 dimensional vector. Okay, so let's go back and let's talk about the advantages of SIFT. It is local, so it will give you a point and it will give you information locally about that point. Since it is local, this part of the feature is local. It is not affected from the other parts of the image. This part is local, not affected. So that means that it is robust against the occlusions. What is an occlusion? Occlusion is this. Occlusion is this. Let's say, what did I say? This part is local and this part is local. Even if I don't see this part of the image, if I don't see this part of the image, I am going to find it, this one, because it is local. It doesn't need the whole image. It is distinctive. Okay, I can match those 128 dimensional vectors with others, and if these two parts of the image correspond, it will give me a very small difference. Quantity is important. It produces many SIFT points. It produces many points on the image. It is efficient. Okay, I can run this close real-time performance on good systems, and it is extensible. It can be used with different feature types. Okay, so these are the good things. So, and these are the steps of a SIFT, steps of a SIFT interest detector. Okay, first we are going to find the scale. We never did this before. Okay, when we did the corner detection, we didn't look at the scale. We never said that if image is large or small and etc. Now we are going to make a search in the scale space, and we are going to find the scale of the feature that we are going to find. Then we are going to find the key points. We are going to say that, okay, this is my corner or this is my specialized point. Okay, that's the key point localization. And then we are going to find the orientation of the key point. We are going to say that, okay, this is the north direction. And then we are going to produce that 128 dimensional vector. Okay, so let's start from the scale space extrema detection. Okay, the goal is here. Okay, I'm going to identify location and scales that can be repeatedly assigned under different views. So whatever the image is, whatever the lighting conditions are, wherever the our points are, we should find the location and the scale of it. Okay, so we are going to make a search in the scale space, and this is what we mean. Our image is not XY image anymore. It is XY sigma. Sigma is the sigma of the Gaussian that we use to change our scale. Okay, so we talked about this image pyramids before. How do we form the image pyramid? Let's say this is a 64 by 64 image. If I take those 4 pixels at the corner, if I take the average and if I assign it as a single pixel to this one, and I repeat this one for whole the image, so I am going to end up with 32 by 32 image. And if I do the same thing here, 4 pixels and average here, it is 16 by 16 and 8 by 8. So the same image is going to be used for producing smaller images. This is called image pyramid. Okay, this is called image pyramid, and we are going to use this idea in many other places. Okay, this one has a very coarse information about the bottom image. I know this one. Okay, I know this one. Before doing this, taking the average, maybe I should apply a Gaussian filter, so I am smoothing out the details. Here is one example. I apply Gaussian and I produce this image and this image. When you look at this image, I can see the man, the head, the shoulders, and etc. But I lost lots of detail. For example, now I cannot see the colors of his eyes. I cannot see. I think these are the paint brushes. Yeah, the paint brushes. I cannot see the paint brushes anymore, right? But general structure is there. General structure is there. That's the idea of the image pyramids. Okay, so the applying a Gaussian and making it smaller is the image pyramid. But what we are interested in this, okay, maybe we should be careful about when I move from this to this place or from this position, this image to this image, what am I losing? If I keep track of it, what am I losing? What is introduced? That would be an interesting point. And Law says that, inventor of the SIFT, he says that I am going to change the scale of the image using this Gaussian. Okay, if I apply Gauss, okay, and after applying the Gauss I will get a new image, right, with less details, and the difference between these two images is going to tell me about the interesting features. That's going to be Laplacian of Gaussian. Remember what was the Laplacian? Laplacian is the second derivative of the given function. Saliha, you have a question? Saliha, do you have a question? You raised your hand.
No, I didn't. My connection was lost,
Okay.
and I was trying to do something.
That's fine. Okay. So the idea of finding the scale of the image is this. Okay. We are going to take the Laplacian of the Gaussian, that is the second derivative. Remember the first derivative? Yeah. No. Maybe I have it somewhere here. Did I do? No, I didn't put it in there. Maybe I can do it myself. Maybe I can do it myself. Okay, this is my Gaussian. Okay, this is my Gaussian, right? If I take the first derivative of it, it's going to be like 0, 0, 0, then I do this, 0 cross, then I do this, like that. And if I do the second derivative is going to be, remember the second derivative here is going to be the 0 cross, right? And because that's the maximum, that's the minimum, another 0 cross here, and then I will have at this point here, at this point there will be a peak, there will be another peak, and there will be another peak here. So it's going to be like, we'll go up and down and we'll come back, peak, and like that. Sorry, it should be symmetric. Let me make this symmetric, more symmetrical. Okay, so it should be like that, goes down and comes back up, and unfortunately my drawing of symmetric stuff is like that. Okay, good. Oh, okay, here it is. So that's the second derivative of the Gaussian. That's called the Laplace, and we did that before. You remember that, right? Second derivative edge detectors. So this guy says that take the Gaussians, okay, of the images, and at different Gauss levels or the sigma levels, and take their second derivatives. That's a good blob detector, they say that. For example, if I take the second derivative of this one after some Gaussian, I can get these blobs. These are the blob detectors. So those blobs will correspond to the central parts of the sunflowers. Okay, and I am going to use this idea. So I will have like the image pyramid. I will have a few image levels. For example, if this is my original image, okay, and I will have a smaller version of it, and I will have another smaller version of it. 3 of them. So this is like a pyramid. But for this image, I will apply a Laplacian of Gaussian operator, and I will get a second image and a third image. For this one, a second image and third image, smaller one. And for this one, second image and third image. So I have a single image pyramid, but for each inside each image level, I have many versions of the same image, and from here to here, from here to there, is Laplacian of Gaussian operator applied. Okay, Laplacian of the Gaussian operator is applied. That's what I do. So this is and these are called octaves. Okay, so I have 1, 2, 3 octaves. This is octave number 1, octave number 2, and octave number 3. Okay, so for the first octave, I applied a Gaussian, and then the second derivative, Laplacian of Gaussian, I obtained this one, and then this one, and then this one. No, but maybe I shouldn't say it that way. Let me go back and let me do this. This is the Laplacian. Okay, so the second derivative of the Gaussian is the Laplacian, the one that I showed you in the blue line. People say that instead of calculating this Laplacian, I could do this. Apply a Gauss to my image, apply another Gauss to my image with a different sigma, take the difference. These two are almost the same. Okay, so either you would take the second derivative operator of a image, or you would apply the Gauss and another Gauss and take the difference. It would be the same thing. So blue one is Laplacian, red one is difference of Gaussians. So we usually prefer this difference of Gaussians because it is cheaper. They are not exactly the same, but since they are cheaper, we prefer difference of Gaussians. So this picture does that. Okay, instead of applying Gaussian, Laplacian of the Gaussian, we do this. I apply Gaussian to get this, another Gaussian to get this, another Gaussian to get this, another Gaussian to get this, and then I would take the difference between these two. So this is difference of Gaussians, but actually I am trying to approximate Laplacian of Gaussian. So I will think that DOG and LOG is the same thing. Okay, DOG or LOG is the same thing. So this is the first octave, this is the second octave, and I can do this as many octaves as I want. Okay, why are we doing this? We are trying to find image features that disappear in the scale space. This is called a scale space. Okay, so this is a scale space. Scale increases this way, our x direction this way, and our, let's say, y direction is this way. Okay, so it is a three-dimensional space. Previously we never looked at this space. We only looked at x and y directions. But now we are trying to see the effects of the scale. When I am moving up in this image, in this three-dimensional image, if I see something new, if I see something interesting, if I see something that is different from the neighbors, then I say that that's an interesting point. That will be my point. Okay, that will be my point. Previously I was doing this with the Harris corner detector in a single image only. Okay, I was taking the Hessian of the image, that's C matrix, and that those lambda values, if they are large enough, the C is large enough, well, in that case, I will say that there is a interesting point here. If that C is larger than the neighbors, now maximal separation, then I will say that that's a corner point. Now I am going to do this in 3 dimensions. I am going to compare it with its neighbors in the x and y dimensions. Also, I am going to compare it with the sigma direction. Okay, x and y comparisons will give me position invariance and rotation invariance. Sigma dimension search will give me the scale invariance. That's the idea of SIFT. That's the idea of SIFT.
Is this sigma same as the sigma used in Gaussian?
Yes, the sigma is the same as the sigma of the Gaussian. And let's say how many S values here? I have a sigma 0, then sigma 1, sigma 2, sigma I, and sigma S plus 1, depending on your S value. Okay, how many sigmas we are going to have? It depends on this S value. Usually we are going to do this. Sigma 0 is going to be 1.6. Okay, then I am going to multiply it with a constant value, and I did increase this 1 by 1 and 1 by 1. So maybe, and there are many experiments about this, which one is better, which one is not. And we will run experiments to decide on what initial sigma value is good and what the values of S should be used for these pyramids. Okay. Doğa, you have a question?
Yes, I have a question. Can you hear me?
Yeah, I hear you.
Okay. After we operate a Gaussian filter to image, and after again with a different sigma, with difference of Gaussian, we are subtracting this image. So we have another image. Are we looking at if there is some features doesn't erase while we are subtracting Gaussian image? If there's something not raisable, we think that that's a good feature. That's a strong feature. Is it right?
Yeah. In this image sequence, in this 3-dimensional world, if we find some features that are different from its neighbors, both at x and y and sigma dimensions, then we are going to mark it as these are very good dimensions, these are very good points, they are very different from their neighbors in terms of scale x and y.
Okay, and are we so we have to map it some before we find a vector that but how can we know? Are we looking at its coordinates? Only coordinates?
Sure, I mean, I know, I mean, we are going to do this at every part of the image. Okay? We are going to do this at every part of the image. On all possible locations in the image. I am going to do this here. I am going to do this here. I am going to do this here, and I am going to do this there. Okay? All possible locations, like we did with the Harris corner detector. And if you find such unique points that are different from x, y neighbors and the sigma neighbors, then I'll say that, okay, this is a special point.
We are only taking the derivative only with respect to sigma, right?
No. I am going to take the derivative. Of course, I mean, what is the well, I mean, I am trying to do the Laplacian of the Gaussian. That is the second derivative of the Gaussian and apply it. But that is expensive. Instead, I am doing this. I am taking the Gaussians of the images and subtracting it from each other. So it's a special kind of derivative.
If we wanted to take the Laplacian of Gaussian, do we take the derivative with respect to x, y?
X and y, yes, that's true.
But I saw on the slides the derivative with respect to sigma, I think.
No, but there is no, well, I mean, if you remember this one, if I take this, okay, if I take this difference, it looks like I am taking a derivative with respect to sigma. That's what it looks like. But I am trying to approximate the Laplacian of the Gaussian. That's what I am trying to do.
Okay.
Okay, the idea is taking the Laplacian of Gaussian with different sigma values. Okay, so what does the Laplacian of Gaussian do? It would find the edges, right? So it is trying to find the edges in the scale space. And if the edge that I find is very different from neighbors, then I will like it. So it is 14:28 now. I am way over my first part of the lecture. So I will take 10 minutes of break. After the break at 14:39 you will have your quiz, okay? It will be two or three question quiz. Çağdaş, you have a question?
Yes, I have.
Sure.
I get that Laplacian of Gaussian find my rotation and translation points, edge points, but I cannot understand that in different scaling. How can I find with Gaussian? Different scale cannot if there is a
Çağdaş, that's a very good question, and I am going to show you how. I didn't tell it to you yet, okay? Because we are going to make a search in the scale space. We are going to find the scale, right? Okay. Okay, time is up. Time is up. Did everybody save the work? Did you guys save your work? Anybody having a problem? Did somebody say no? Did everybody save their work? Okay. Okay then. Okay, let me continue with my lecture then.
How much this will affect?
I don't know. Maybe it won't. I don't know. It affects the rest of the lecture because nobody was answering me before I said that there is a quiz. Okay, so I'll see. So this is the I think I'm going to do this from time to time. This is the general structure of laws pyramid scheme. There are different octaves, the first octave, second octave, third octave maybe, and you keep applying increasing Gaussians to the image and take the differences. Taking these differences is like trying to find the edges with some threshold. But now this is what we are going to do. We will take this stack of images, okay, and we will make this comparison. Okay, we will find the maxima and minima of the difference of the Gaussian in scale space. Take this cross, for example. I will compare this against all these 8 neighbors, 1, 2, 3, 4, 5, 6, 7, 8, in the same scale. And also I will compare it with the 9 neighbors in the upper scale and 9 neighbors in the lower scale. Okay, so a total of 26 neighbors in the x, y, and sigma scale. If this point is larger than all of them or smaller than all of them, then that point must be unique. That point must be a special point in terms of x and y dimensions, also in x, y, and sigma dimension. Okay, if I find such point, that means that I find the xy location in the image. Also, I find its scale in the scale space. So I am both finding the location and the scale. We used to do this with the Harris corner detector only in a single image, because in Harris corner detector we don't consider the scale space. Okay, this is how you find the scale. This is how you find the scale. We find in a way that, okay, this is responding much better at that scale, so I find it. So once you find the scale, you know how large your window should be, and that's going to help you a lot. That's the key point localization part of the SIFT key point extractor. Okay, so how many scales per octave, how many scales should I look at? People did experiments. Okay, people did experiments, the final experiments. They found that, okay, number of scales per octave is maybe optimal around 3. So 3 scales here, 1, 2, 3 scales. Oh no, like this one. This is 1 scale here, 2 scale, and 3 scales. So total of 4 images. When I look at these images, it's going to be optimal for that experiment. Okay, how many scales per octave? Also, what is the initial value of sigma? They did experiments and they say that maybe 1.6 is the good trade-off. Okay, so I think somebody asked this question: how should I make the decision of the initial sigma value and how many scales should I have? These are all decided by running these kind of experiments. Okay, so key point localization is, okay, once a key point candidate is found, okay, we say that I find the location and I find the scale. Okay, and by fitting a three-dimensional surface to that area, maybe I can find the principal curvatures, but I'm not going to go into details of that one. Okay. Good. We still like to run the Hessian matrix here to eliminate edge responses or the flat area responses. So we don't run this expensive algorithm on places where there is no corners. Okay, so we run this only at places where there is a chance of having a corner. Okay, and this is done in a regular way. So at this point now I have my x position, y position, and the scale, and after that I need to find the direction orientation of the window. Okay, Çağdaş, you have a question?
Yes, I have. I want to ask that how can I determine my scaling ratio? Scaling ratio is, I think.
What is scaling ratio? Did I hear it right? Scaling ratio?
Yes.
What is?
We told about one image and it scaled another version of it.
Yeah.
But what is the scaling ratio? Because if my scaling ratio is 1/2, but which point which I search is scaled about 1/10, I cannot find it anyway again.
So by scaling ratio, I mean, you mean these scales? What is scaling ratio?
I take Gaussian derivative of image, and for the obtaining difference of scaling of this point, I need to use my another scaled version of it, but I understood false.
Well, I mean, if you are talking about the octaves, okay, I have a number of octaves, 1, 2, 3. Depending on your experiments, which one is better. Usually you use 2 or 3, okay. But if you are referring to your the parameters, Gauss parameters between these the parameters of these images, this is the formula. You start with a sigma 0. For your first image, you apply this sigma 2 to the power 1 over s sigma 0. Then this, and at the top you would find 2 to the power 2 over s over s sigma 0. What is sigma 0? By running the experiments, I find it to be 1.6. What is s? S found to be 3 is the best. Okay, so this is how you choose your sigmas, and for your octaves you use the half the size of each dimension. So half the x dimension, half the y dimension. Totally, it is 1/4 of the image size of the original image.
Okay, all right.
Okay, so this is how you do the x again. X and y location, I already know how to do that with the Harris corner detection. For the scale, I am doing this SURT, and which is expensive actually. It is not that cheap. Okay, we did the key point localization. Of course, we are not doing this in a blind way, as I said before. We calculate these experiments, we calculate these values, and if there is a edge, then I calculate all of these. So flat regions, edge regions are eliminated. So then we are going to do the orientation assignment. Let's say I have found a window. Inside that window, there is an interest point. That interest point has higher or smaller values than the neighbors, all of those 26 neighbors. And I like to know the direction of this window. So this is what I do. I take this window. Let's say my window is 16 by 16. Okay, so there are total of 256 elements in this window. I calculate the gradient angles of all the pixels inside this window. Okay, I calculate them, and I make an histogram of size 8. Okay, this is 1, 2, 3, 4, 5, 6, 8. That means that I divide this from 0 to 180 degrees into 8 intervals. Okay, are there 8 or 7? 1, 2, 3, 4, 5, 6. Okay, there are 7 here, but it should be 8. Okay, it should be 8. So I make this histogram. This one says that from 0 to 20 degrees there are, let's say, 10 elements. From 20 to 40 degrees there are 30 elements, and then I have 20, then I have 8, 15, etc. So when I look at this one, I would say that from 20 to 40 is the highest, so this must be my orientation. So I know that in this window my orientation is between 20 and 40 degrees, maybe 30 degrees. So I know the orientation of the window now. So I know 4 things: x position of the interest point, y position of the interest point, scale of the interest point, also the orientation of the orientation point. Sometimes we may have more than one. For example, it could be like that. Okay, both of them have the same number of elements in it, so we will have 2 major orientations. It could happen because in a corner like region there might be more than one orientation. So I'm going to produce two interest point with different orientations. So I have the orientation 2, and these are some examples actually. These are some examples. If this is my original image, okay, after that I calculated my XY sigma values for each key point, and as you see, I assigned the orientations for each of them. They have orientations, also they have their scales. See, there are two arrows here. One is there, so it must be that two orientations are dominant here. Some of them are very, very small, some of them are large. For example, this one is very, very large. Okay, so this is the initial one. Then after the key points, I apply the gradient threshold. I only like to have contrasty feature points, and then I do this ratio threshold, which comes from the Harris corner detector. Okay, so this is just one example. So what did we say about the SIFT? We said that quantity. There are many SIFT points on this image, so there is plenty of chance for key point correspondence between images. Okay, so that's the end of the first part of the SIFT. So we detected the key points, we find the XY scale and the orientation, and now we are going to move to the key point descriptor, that is a 128 dimensional vector. Okay, any questions? I think I had some other slides from some other people. Let me try to find it. It has some nice where is my is it in here? Yeah, more slides, but this is not in. Okay, maybe. Okay, I am going to open it with PowerPoint. I am going to show you so this is a good example actually here. Just turn it off. So this image and this image, I like to find these two key points, but as you see, the key point around here is larger on this image but smaller on that one. But I like to find the scale of this one. So what I do is I measure the scale of this window and that window. I measure the scale and measure the scale. As you see, so I'm making a search in the scale space. As you see, this guy says that I am making a maximum here. This guy says that I am making a maximum. So their scale values are different. But when I normalize them and put them next to each other, I find this. As you see, the area of the square is the same in both images. I mean, the area inside the square is the same for both images. Okay, good. And the signature function, we talked about it. Do we? Well, I think this is a good one. Again, applying the Laplacian of Gaussian on this image, and this is the maximal point. Some details get lost, some details are becoming more pronounced. For example, let's look at, yeah, that's an interesting, whatever creature this is, I don't know what creature is this, but it looks like, I don't know, whatever it is, it has an eye, right? Okay, look at the intensity of the eye. It is not much, it is high, it is not that high here. So for that, if there is a corner point, or if there is a SIFT point in there, I think its scale would be, I guess this one, because this one is more brighter than this one and both that one. Okay, so that's how you know the scale of it. At the low scale, it is not pronounced. It's a little bit better. Highest, it gets low, and now I lost it. So its scale is not that high, but it is not as low as the initial layer. So that's a good.
So when find, I think it's octaves, right? We apply Gaussian, but does the size of the kernel also change with sigma? Or
of course, sigma is the size of the kernel, Gaussian kernel.
So okay.
Okay, and here in this case, we are not applying the Laplacian of Gaussian. We are taking the differences of the Gaussians. Remember?
Okay.
Okay. By the way, this is a good one too. So if I have a Gaussian like this red one, another Gaussian like the green one, if I take the difference, what do you see? I see this blue line, which looks like Laplacian of Gaussian, but it is actually the difference between these two Gaussians. It is very similar, and it is cheaper to calculate. Okay, am I okay? I think I did that one. Yep. Okay. So see this one, the bright points. There are some bright points at the low scale, upper scale, and so bright points are, for example, this one, very, very bright here, this one, but it is gone in that one and that one. So that the scale for this one is, I don't know where it is. I think this one, this point, the peak, the tip of the beak of this chicken-like creature. Okay, maybe. Okay, and this one here at the largest scale is bright, but here there are some bright points at the low scale. So it changes. Again, SIFT considers the scale of the features. Once I have the scales of the features, let's move to the keyboard descriptors. Okay, I have the location, scale, and orientation. Let's try to compute the descriptor for the local image region. It's going to be dependent on the histograms. Okay, histograms. First, I rotate the window to a standard orientation. If my window is like this way, okay, I am going to rotate it, and it will be like this. Okay, and I'm going to scale it to, for example, to 16 by 16 image. Okay, so whatever it is, this could be maybe 50 by 50, or sometimes 10 by 10 image. Now I'm going to scale it to 16 by 16. Also, I am going to rotate it so that the top part is up. Rotate the window to standard orientation and scale the window size based on the scale at which the point was found. So it doesn't matter now. What kind of scale I have found. All of my descriptors will be in the same scale now because I normalized them. If the scale was large, so it was 50 by 50 image. Now it is 16 by 16. If it is small, then 10 by 10. Again, it is like that. Okay, and then law does this. It says that take your window, again it's going to be a large window. So law says that take your window, if this is your window, divide it into 8 regions. Okay, divide it into 8 regions, and each region, okay, and each region, remember I said that this is 16 by 16. Let's say this is 16 by 16. So this is going to be 4 by 4 each of them. And in each of them there are this many pixels, 16 pixels. Okay, if I take this area, like this area, and enlarge it like that, I'm going to say this. Okay, there are 16 pixels and each one has its orientation. Find the dominant orientation by taking a vote. Ask each of them which direction are you. They will tell you which direction, and whichever direction has the highest vote will be the direction of this 2 by 2 window. Okay, so I am going to take an histogram of each of them. This part of the histogram, okay, what do I mean by histogram? Histogram is going to be, for this part, as I said before, I am going to divide it into 4, 8, okay, 0 degrees and 180 degrees. This one, for example, this one says that I am 30 degrees, so I am going to increase this one. This one says that I am 90 degrees, so I am going to increase this 90. Okay, this one says that 100, again, I am going to be 0 degrees, so I am going to be like that. And this one says that, so I will increase this. This one says that I will do this. So it's going to be an histogram. Histogram is going to be like this. Okay, so this is the dominant direction of that window. So this is what it is showing, right? This one says that this direction is the dominant one, this direction dominant, this direction is dominant, this direction is dominant. So each of these will have an 8-dimensional histogram. 8-dimensional histogram, 8-dimensional histogram, 8-dimensional, and 8-dimensional. What does that make? So this is total of 32. Okay, so this corner has 32 numbers in it. This one 32, 32, and 32. There are a total of 128 values for a window. That's where the 138 comes from. Okay, but I use a normalized region about the key point. By normalized I mean I apply a Gaussian to this point in the center. So in the center everything is more pronounced. Around the corners their effects are lower. Okay, weight them by the Gaussian, and I use the normalized region about the key point. I don't want to use very dominant gradient magnitudes, and I calculate the orientation histogram over 4 by 4 subregions of the window. Okay, so at the end I have a 128 sized descriptor for that 16 by 16 window. Okay, so that's the end of the algorithm of SIFT. It is used in many places to calculating homography between two images, two planar images, and we are going to see it for calculating the fundamental matrix when we are looking at the stereo. Okay, and we use it for 3D construction, motion tracking, object recognition, and etc. So we did something that builds on top of the Harris corner detector, but unlike the Harris corner detector, it is insensitive to scale, because I mean it works much harder than the Harris corner detector, right? Harris corner detector doesn't take scale into consideration. It runs the original scale. That's it. This one tests this thing on many different scales, and it finds the critical scale, and different from the Harris corner detector, it develops a descriptor, 128 dimensional descriptor, and you could use this descriptor to match points between two different images. Okay, good. Any questions? So Opencv says that, okay, I have SIFT, I can give you SIFT. By the way, SIFT is a patented, there is a patent. The patent is held by law, okay, a Canadian university. So it is not free to use. If you are using SIFT in a if you are using SIFT in a commercial application, you are supposed to license it from that university. That's not very good. So there are free alternatives of SIFT, and we may see some of them. And there are other people with SIFT. For example, it is not fast enough. So that's why they developed this new algorithm named SURF. SURF is like SIFT. It follows the SIFT footsteps, but it is faster than SIFT. Okay. So SURF is a faster version of SIFT, you could say. And FAST is another faster algorithm. SIFT and SURF, they are not fast enough, especially for real-time applications. FAST is faster than both SIFT and SURF. And then there is this brief. Brief says that I will not use very large memory locations, or I don't need very large memory resources like SIFT and SURF. 128 floating point numbers is large, so I will use only binary representations, and it will be smaller, so that's brief. And then SIFT, SURF, fast, brief, okay, they are all good, but they are not free. Okay, then they have introduced a open source and free to use version called ORB, oriented fast and rotated brief. Okay, it is fast and it is free. And Opencv, this is invention of the Opencv actually. Opencv suggests using this ORB. And then Opencv applications, you have the, of course, feature matching functions. You give lots of features, interest points, and it matches them. There are two of them. One is the brute force matching. The other one is more intelligent one, hashing based one, is called FLAN. Let's look at some of them. Keypoint detectors of Opencv. Opencv keypoint detectors. SIFT code for the Opencv doesn't come with the Opencv by default. You have to download it. Okay, I have the Harris corner detector. I have, where is my SIFT? I think I looked at this tutorial thing. Maybe this one, yeah. Yeah, so this Harris corner detector, I think, how is the interface to the Harris corner detector? So nicely it gives me all the documentation and same thing. So given the image, find the corners. What are these parameters? 2, 3. What do you think those parameters are? Can somebody tell me what do you think these parameters are?
The one you asked on the quiz?
No, you mean the lambda 1, lambda 2?
Yeah.
No, those are not parameters. Those are the produced things. 0.04 is the lambda. Remember lambda? Lambda is the one that you use in calculating the C. 2 and 3 could be the Gaussian
Sigma, I think.
Gaussian values, but not two dimensions. Let's look at the documentation. I wish I opened it in a, okay, let me open it in a different tab. Okay, I open it in a different tab. As you see, okay, these are the detected corners with the Harris. It's nice, right? So it is finding those corners, and the corners here, I don't find the corner here because this one doesn't look like a corner. It's a surprise. I don't know why there is no corner here. Okay, so let's look at the documentation of, so it's the block size. Oh, okay. So I need the this side of my neighborhood side. Am I running this algorithm? Remember those sigmas? Am I running this in a 5 by 5 window, 7 by 7 window, etc.? Okay, what is K size? Aperture parameter. Okay, so it is the aperture parameter for the Sobel operator. So I am taking the derivatives in x and y direction, but what will be my derivative operator size? And okay, this is the K value, that is the alpha value that I have used. Okay, this is the Harris corner detector. Good, as we know. And there is another corner detector. I am going to skip that one, and this is my SIFT. Let's look at SIFT and surf and fast, and let's skip brief and let's look at the ORB. And I am going to look at the feature matching, the brute force matcher and the flam matcher. And this one is Harris, this one is SIFT. For some reason I am using the same visuals as these guys. Okay, you remember this? These are classical figures. Okay, so I get the gray level image, and I say SIFT detect gray and none. What is none? I don't know. And then I draw these. See, it finds a feature here, and its direction is that way. And this one has two directions. Remember, we said that there might be more than one direction. It might be more than one direction. So there's SIFT detect, SIFT.detect, SIFT create detect. Where are the parameters for SIFT? As I said before, this is not standard part of the Opencv library because it is licensed. The documentation is not that good. That's why I couldn't go in. I cannot click to this one for some reason. CV dot SIFT create and SIFT detect. I couldn't go there. Sorry. And this one is the surf. So the advantage of surf is it is again fast. Why is it fast? Because it is using lots of box filters to make this approximation of the Laplacian of Gaussian, instead of taking the Gaussians and taking a difference. Okay, so in a more smarter approximation way, okay, it is doing this and calculating the orientation in a faster way, and it looks like SIFT is say that I found this larger feature orientation is this way. So the position, orientation, and scale, four things, and each one has their own descriptors. And if you don't like, you can turn off the orientation, and it will be much faster. Okay, that's the surf, and this is fast. Okay, fast is running a completely different algorithm. Around each point, it is looking at the circle, and if the points along the circle they are all different from the center one, then I would say this is a corner. That's the idea, and it is doing this in a smart way. And these are the fast points, very quantitatively a large number of points. Okay, and then orb is an efficient alternative to SIFT and SURF. It is not patented. It is running. An example is here. And finally, I'm going to look at this matching stuff. One of them is the brute force matcher. The other one is a flan matcher. How do you match two images if you have the let's say I have an image like that, this image, and this is the second image. So it looks like whatever this box is in a different position. It is rotated, it is much smaller, and I like to find a correspondence between these two images. And I think this one is using BF matcher. Okay, it is sorted and draw matches. This is brute force matcher. CV normalized Hamming distance. Okay, it is using a Hamming distance, and by default I guess it is using I think by default it is using ORB, this BF matcher. Is there any way to, what happened? Is there any way to use different, matchers, different key point extractors? Sorry, let me see if I can see it. Norm descriptor, BF matcher and algorithm. Okay, BF matcher, create orb. Okay, normalization type are preferable to SIFT surf. Do I have any other? Okay, I didn't find how I changed the key point detector or descriptor, but it looks like it is.
I think we give the key points to it.
Does it? No, it doesn't take the key points. Does it take the key points? Oh yeah, I didn't look at this part. That's true. Okay, yeah. See, it uses the orb create, whatever you call it, or the SIFT create, orb create, surf create. You get your results. Okay, out of these orb results, you get your key points and the descriptors. Okay, I have two images, box image and box in a scene image, and I get the key point and the descriptors for both of them, and then I match these two, descriptor 1, descriptor 2, using the brute force matcher. Okay.
The Hamming distance there is for the vectors, the descriptor vectors, right?
Yeah. How to compare those two? Hamming is the, I guess Hamming is the, is this the default? No, it is not. It is not default. What are the alternatives? I have Hamming distance, I have
L1 and L2 distance.
okay, L1 distance, L2 distance. Okay, I don't want to go into details. You guys look it up. Okay, L1 is here. L2 no. L1 is here. L2 is here. Hamming is here. Okay, Hamming 2. What is the difference between Hamming and Hamming 2? In of the from 0 in case of two input arrays, calculate Hamming distance between the arrays. Single bit. Okay, you guys know the Hamming distance, right? Hamming distance is good for comparing two binary stuff. It's like x over kind of comparison. It's fast if you are doing it that way. Okay, anyway, so these are the Opencv implementations of all those feature detectors and descriptors. I think finally they are running this. Okay, with the SIFT. You SIFT create and SIFT detect and compute, and this is a brute force matcher with KNN match. I don't know the difference. You need to read it. Flan is the smarter one. It doesn't do this matching in a brute force match. It doesn't try to match one with everybody else. It uses a hash table. Okay, and is an example.
Flan doesn't compare all possible pairs, so it should make a estimation, right?
No. It's perfect. It's like making a binary search in an array. You sort your array first, okay? Then your binary search is very fast, right? So there is an overhead of sorting your array first. So this is called binary. This is called two-dimensional hashing. You give your two-dimensional points to a function that prepares them for efficient access, and after that matching these two sets becomes very efficient. It is not so the final result should be as good as the brute force match, but there is an initial cost. Okay, good. So let's take 10 minutes of break. After the break, am I done with this? Yeah, I am done with this. After the break, we will start talking about line detection and circle detection in our next chapter. 10 minutes.
Bismillahirrahmanirrahim.
Okay, people. So we are still trying to do some feature detection, primitive structures in our images. We started with edge detection, then we moved up to corners, and after the corners we try to find more meaningful image features such as the SIFT points or SURT points or ORB points. Now we are trying to look at more higher level structures such as lines or circles or arbitrary shapes such as this one. This one is not drawn yet. I like to find the border of this structure, which is the CT image of a human heart, and this red contour that I have drawn indicates the inner wall of the heart. If you find the red contour, then you are going to, maybe you may calculate the volume of the heart, inner part of the heart, so that I can find the amount of blood that is being pumped. So now I am going to find higher level features of the images such as lines and circles. Let's start with the lines. So we are going to call this model fitting, line and curve detection, maybe. Okay. Grouping and model fitting, they are involved in line and circle detection. Of course, let's say I have an image like this one, and I have detected many edges or points of interest. For example, this is an edge. It has X and Y location. It has also it has the orientation, right? It has one orientation, another edge like that. I have unrelated edges like that. Okay. Let's say there is a circle and I have edges like those. So I like to find circles and the lines in this picture. If I know that these edges are related, if I can group them together, maybe I can fit a line on them, right? I can fit a line on them, and I can find the line that goes through these edges, but I don't know if they are related. So grouping is a problem. If I can group all these edges together, maybe I can fit a circle and find the circle to it, but I don't know, because all I have in this image are these detected edges. Some of them belong to the lines, some of them they don't belong to the lines, some of them are from the noise, and etc. Okay, so grouping and model fitting, they come hand in hand, and it is not easy to group them together without the model fitting. Okay, for example, if somebody tells me that okay, this black line is your line, so all the edges that are close to this black line with the correct orientation are your edges. If somebody tells me this, then that would make my job a lot easier, but there is nobody saying such a thing, so I don't know. So I have to be smarter. I have to solve these two problems together, at least for the line detection problem. Okay, so how do I detect the lines on images? Let me copy this. And paste it in the slide now. Okay, so how do I find the lines on this image? One idea could be this template matching. Okay, I will put a theory, I will make a proposal, I will say that okay, if there is a line in this image, okay, if there is a line in this image, it could be between these points, right? It will be between 2 points. Let's say one point is here on the corner, the other one is here, okay. I would draw this line and I would count the edges that correspond to this line. How many lines in this, how many edges on this line? 0. So that's not a good line then, right? So that didn't work. That didn't work. So how about the next one? A point, a line from this point to this point. Would this work? Well, it looks like there is an edge that is on this line, but the orientation doesn't fit. So I couldn't find it. Okay. So how many times do I try this? Let's say I have 100 by 100 image. So how many lines can I draw between from this end of the image to that end of the image? So 100 points here, 100 points there. So there are total of 10,000 lines between all the points of this end and all the points of this end. And maybe I can do the same thing between these two lines too. So it is times 2, there are total of 20,000 lines, possible lines. And for each of them I will calculate the line and I will count the number of edges that correspond to that line, and I will say that okay, this line has enough number of edges on it, so it will be okay. So it looks like one of the lines would be this one, the other line would be this one, and the rest it will not work. They will simply won't have enough number of edges on it. So did you like this idea? This is called template matching. Did you like this idea?
It's good, but it looks very expensive.
Yeah, 20,000 lines for this simple 100 by 100 images. It is expensive. First you do the edge detection, then try each of them one by one. That's not good. Also it ignores something actually. This one will not tell me where the line starts and ends, right? And I'm running this from one end to the other end. I guess those are the problems. We don't like it. Doesn't scale very well. Okay. By the way, each line is a loop. Okay. So all these 20,000 lines, for each line I have to test it. I have to say that okay, on this line, is this edge on this line? No. Is this edge on this line? No. Is this edge on this line? No. So it is like 20,000 times number of edges. How many edges I know? I don't know. So I have to test it. And that's not going to be good. So how do I do this testing? If let's say this is my line, I know the formula. So the line is going to be y is equal to mx plus b, right? Or mx plus n. So I know the m and n values. Okay, let's say this point is 100 by 100. So I am going to say, is 100 equal to m 100 plus n? I know the m and n values. Okay, if it is the same, almost the same, I will say yes. So checking if an edge is on the line isn't a very difficult thing. It's just multiplication, addition, and comparison. That's it. So it is not that difficult. So I know that one. But I can do much better than that. It's called Hough transform. Okay. This is a guy, the last name of the person. Okay. This guy is a physicist. Okay. He's not a physician, sorry. He's a physicist. and he developed this technique for tracing the atomic particles, I guess. Okay, and he said this, maybe we can do this instead of hypothesizing lines like that. I will take an edge, for example this edge. What is this edge? Let me take this one. Let me take another one. Let me take this edge. This edge has a coordinate of 30 by 30, right? 30 by 30. And single edge, how many lines would go through this single edge? Okay, I will ignoring the orientation. This is one line, another line, another line, another line, right? How many lines go through this edge? Theoretically, in a continuous world, there are infinite number of lines, right? But all of them should satisfy this. All of them should satisfy y is equal to mx plus n, right? And I know that on all of those lines 30 is equal to m times 30 plus n, right? All of these black lines should satisfy this equation. Each line has their own m and n values, but whatever they are, it should be satisfied by this equation because they all should pass through this 30-30 point, right? So let's look at this one. What is this? What kind of equation is this?
Linear.
It's a linear equation. So what does that mean, Resul? So it is it's a formula for what?
We can formulate as matrix multiplication, I think.
Well, no, you don't have to think that complicated. It is even much simpler than that.
It's still a line formulation.
It is a line formulation, right? I mean, this line was in XY coordinate system. This is in MN coordinate system, right? So this is like, if this is M and this is N, okay? In the MM world, this is a line, right? Let's draw a line. So let's give M 0. If M is 0, what is N? N is 30, right? So this one. If M is 0, N is 30. If N is 0, what is M? M is 1, right? Like that. So this is 30. This is 1. So if I draw a line that goes through like that, doesn't look like a line. Okay, let me try to make it a, this is even less linely. This is best I can do, sorry. Okay, so that green line represents all the mn values, that this line can have. What does that mean? Pick a black line here, calculate its mn value. It has to be on this. It has to be on this line, right? On this green line. Is that correct? So where are we going now? Any question?
Yes, I have a question. Here, if we take a M and N point that is on the green line,
Yeah.
it will be in our space.
Yeah.
It will be on our space line. Is it correct?
Yes,
Right?
just pick a point, for example, this point, okay, M and N pair, okay. That M and N pair will make a line like that, and that line has to go through this 30 point, okay, and it has to be one of these black lines.
Okay, thank you.
Okay, so put all of these black lines, take their M N values, it will make this green line in this space, M N space. So that gives me an idea. I will do this. If this 30 point, all the lines that goes to this 30 point, what are they? This is the green line, right? All the lines that go through this 30 point is the green line. Let's look at this one then. Let's look at this one. Let's say this is 50 and 10. So all the lines that go through this 50-10 will be like this. Okay, let's write it then. So 50, no, M times 50 plus N is equal to 10. Okay, if M is 0, then N is going to be 10. Okay, so if M is 0, N is going to be the 10, that's from point. And if N is 0, M is going to be 1/3, so it's going to be here, right? So what do? I draw this line will go there and it will intersect here. Okay, so this second line, the line that I have drawn with, I am sorry, I messed up with the colors. The second line, let me make this red line. Okay, the red line and the green line will intersect at some point. What does the red line represent? Red line represents all the lines that goes through this 50-10 point. Green line presents all the lines that goes through this 30 point. Okay, so what does that mean then? If I intersect these two, green line and red line, what is this? What is this red point? This
The
red
line between
yes, the red
points.
say that again.
The line between the edge points.
Yes, the line that connects this 30 point with the 50-10 point. Okay, it is this. Let me use a red color. It is this line. Okay, so that intersection will give me this line. That's the idea. That's what I'm going to do. I will take all the edges that I have detected. I will take all the edges that I have detected in this image, and for each edge I will draw a line on this MN space. Okay, MN space. Suppose I did that for all the edges on this line, and all those lines has to pass through this point. Okay, so whichever has the highest intersection number will give me the MN number of this line. That's the idea. That's the Hough space. That's the Hough transform. It will transform to a different space. Okay, that's the Hough transform. That will give me the lines.
That's very interesting point of view.
Well, yeah, the voting is always different. I mean, voting when you do the voting of local data, whoever gets the most vote will be your final result. Is an interesting idea because You may ignore the noise, you may ignore the occlusions, and everything can be done in parallel. It has lots of attractive properties to it, and we are going to use the same idea to detect circles, ellipses, and arbitrary shapes. Okay, good. So let's look at the details. I mean, when I say this intersection, how am I going to find the intersection of so many lines? Of course, I am not going to draw these lines in a simple MN space. I am going to make a M. For some reason, I cannot write M today. When I am writing M, I am doing this. I am putting one more hump. That's funny. Okay. This is M and this is N. Okay. So I am going to make a two-dimensional array like that. Okay. Two-dimensional array of counters. And if I am drawing a line like that, instead of drawing a line, I will say, okay, instead of drawing a line, I will say, this is 1, 1, 1, 1, 1. I am incrementing the counters along the line. So this is not a line anymore. Okay, I made these lines. And there is another line here. So this is 1, 1. Now this is going to be 2 and 2 again. 1, 1, 1. See, wherever that line goes, I increment those counters by 1. And if I do it with the third one like this, so this is 1. All the spaces are, all the empty spaces are zeros. 1, 1. Now this one is going to be 3 and 1, 1, 1, 1. Okay. As you see, this one has the intersection. It has the highest number of votes. Okay. So my task is get all the edges. For each edge, draw a line on this voting space, MN space. And after all the voting is done, go back and find the maximum number. Okay. This one says that, okay, at this point here, which is 1, 2, 3, 4, 4 and 1, 2, 3, 4, 5. 5. The position 4 and 5, M is 4, N is 5. There is a line, okay? This line has 3 edges on it. I know that one. At least 3 edges on it. Okay?
So it's like a we do this for every edge, right?
Yeah, we draw a line for each edge. So this is much cheaper than what we did before. Previously, what we did, we hypothesized 20,000 lines, and for each line, we checked if all the edges are on it or not. Now we are doing, for each edge, I am drawing a line. Okay. So drawing a line means that in the MN space, I am incrementing some counters. How many counters can I increment at most? You could increment at most n square plus m square square root number of, if it is a diagonal, right? Elements. So it is on the order of n plus m, something like that. So the complexity is much lower than this, much lower than that. Yes?
I didn't get that. So why does one edge point, does it correspond to one line in the NM?
Yes. Remember this 30-30? For the 30-30, how many lines are there? Infinite number of lines, right? So how do I represent all those numbers? By drawing a line in the space, for example, this one. Okay, this green line represents all the lines that goes through 30-30 in my XY space. So for each edge, I am going to draw a line. So this line introduced a line, this edge introduced a line, this edge introduced another line, this edge introduced another line. If I put them together,
Oh, okay.
okay, I get the intersection.
It's like a histogram for mine.
Two-dimensional histogram, you could say, yes. Yeah, that's exactly what we are doing. And you are voting, you are incrementing the histograms for each nm pair, okay? For each nm pair. And at the end, you get the, you try to find the, you pick the nm pair that has the most votes. Okay, so let's go back to the slides again. So instead of going directly for the solution like the templates, we do a voting technique. A line, of course, can be specified by this. You learn this from your middle school years, 10 years ago, 15 years ago, whatever. Okay, this is the formula for the line. That's good. So mn space is a two-dimensional space. That's nice. That's good. And let's say in my xy space, I have 2 points. One is here, one is there. Okay. Let me use a different color. This is the green one and the red one. The green one is 20 equal to 20 is equal to 20 is equal to m times 10 plus n, and this red one is 60 is equal to m times 30 plus n. So okay, so this is a line and this is a line. Okay, so which one is in the mn space? This one 20, m is 0. If m is 0, n is going to be 20. I guess it is this one. So the green one is this one. Green one is this. And the red one is, I guess, oh, I am making a mistake here, right? Which one is green? Is what I'm saying? Okay, let's look at this one, 0 part. When m is 0, n should be 20. Is this? Okay, I think it is correct. Yeah. And the red one is here. And this is the red one. So red line represents all the lines that go through this point, and the green line represents all the lines that go this point. How about this one, 2, 2? What is 2, 2? 2, 2 is the mn pair. It should represent a line, right? What line is that? It is this line. Okay, it is a line that goes through both of these points. Okay, so I just repeated what I said before. So let's look at this in a voting space. Let's go to there. Okay, I have this image. Okay, it is, I guess, 70 by 70 image, and I did my edge detection. Edge detection results are those. When I look at these, I see two lines. Of course, I have a much more complex visual system than these local algorithms. I see these lines now. Okay, do you see another? Maybe if you force it, could this be a line? Yeah, maybe. And do you see anything? Maybe if I force it, this could be another line there too. I am not sure. But there are two dominant lines, I know. The other ones are not dominant. If I make a vote, if I take a voting procedure on the M, N, and the counter space, M, N space, this is what I would get. So each edge is drawing a line in the space, and it is incrementing the counters by 1. So what do you see after all the voting? I have one peak here, another peak there, and there are some noise kind of peaks. What are those? Well, any 2 points, for example, these 3 points, they are in line by coincidence. It's going to cause a high peak. It's going to get 3 votes, right? Or maybe this one is going to 1, 2, 3, 4, 5. It's going to take 5 votes. Okay? But the higher ones, if I take a good threshold, like anybody about 10 is my line, then I should be fine. So this one automatically finds you all the lines with strong evidence, supporting edge evidence. It doesn't matter how many lines you have in the image, it's going to find it. And the nice thing is that it is not sensitive to any breaks in the lines. For example, this part is missing, this part is missing. So any occlusions, for example, there is an object in front of my line, there is another object in front of my line, I could find them. Okay, this is called line detection by Hough transform. And this idea could be applied to any geometric shape as long as they have this kind of closed form or parametric form formula. A line has a two-dimensional space, M and N. Okay, so I am going to make my voting in a two-dimensional space, M and space. How about a circle? When I do the circle, how do you do the circle? Circle is x minus a square plus y minus b square is r square, right? So how many parameters do I have to define a circle?
We have to know x and y parameters and our parameter.
So there are total of 3 parameters. So
yeah.
I am going to make a vote in 3-dimensional space, A, B, and R space. Okay. So it is a more complicated voting operation. I need lots of data and lots of memory, etc. But again, I can do that. So any closed form formula, if it defines my geometric shape, I can use the Hough transform to find those. Before I go into the details of line detection, let me go to the Opencv implementation of the Hough lines. Opencv Hough transform. It is not Hough, okay? It is Hough. The name of the guy is Hough, okay? Don't change his name. Okay, this is Hough circle, Hough line transform. So let me image read, check it, Kenny. It first does the Kenny edge detection. You get the edges and you call this Hough lines, okay? And destination lines, and you specify the range for the lines. And let me, do we have, okay, yeah, okay, here it is. Okay, and this image, well, of course, this is an edge detected image. You find the results with the Hough lines. So let me go to the definition of it, if I can. So it is image is the input, lines are the output. Rho theta threshold. Okay, well, I didn't give you the exact algorithm yet. When I give you the exact algorithm, I will tell you what these are. Due to some problems with these MN space, okay, we don't make a voting in MN space. We don't like MN space. Instead, we will switch to polar coordinates, okay, and this polar coordinates voting is much more convenient, and we are going to do it next week. Okay, are there any questions? Remember what we are trying to do. We detected edges, and then edges are primitive, then the corners more complicated, then corners with descriptors and the scaling sensitive corners, etc., SIFT, SURT, ORB, etc. Now we are talking more about using the edge detection results. We are talking more about lines and circles and arbitrary shapes. Okay, after that I am going to stop, okay, because it goes like that. After that I am going to stop and we will start talking about multi-view geometry of the camera system, more than one cameras. Okay, if there are no questions, that's it for today. Okay, I'll see you next week.
Thank you.
See you.
Thank you
Bye.
very much.